Hello. In this revision video, we're going to look at the concept of resistance, the use of Ohm's law to calculate resistance, and the use of resistors to control resistance in a circuit. So we're going to start off by quickly recapping on three terms that we've been introduced to in a previous video in this series. There's a link to this video in the top corner. So firstly we have power, which is the amount of energy used over time. So this could be the amount of electricity that's turned into light and heat in a light bulb per second. Secondly, we have voltage, and voltage is the amount of potential energy available. So for example, you'll have the voltage written on the side of a battery. And then finally we have current, which is the rate in which electricity flows through a circuit. And these three terms relate to each other as shown in this formula. So power equals voltage multiplied by current. So if you know the voltage and the current, you can work out power. Or if you know power and voltage, you can work out the current and so forth. We can write this in short with P representing power, V voltage, and then I for current. So in this video we're going to look at resistance, and this directly links to the current or the flow of electricity. Now, some materials are better conductors than others. This basically means that some materials allow electricity to flow through them much more easily than other materials. This is the material's conductance. So if we understand that concept, then we can flip it upside down and look at it from the opposite perspective. Because if different materials allow electricity to flow at different rates, then we can flip it around and say, well, different materials must then resist the flow of electricity through them at different rates. And this is what we call resistance. So resistance is the opposite of conductance. So when we talk about a material's resistance, we're talking about how much that material resists or slows down the flow or the current of electricity. And different materials have different resistance. So to try and explain that, we're going to use a metaphor of a hose connected to a tap. So the tap represents the voltage. The water pressure coming from the tap is the potential energy, whereas the water flowing through the hose represents the current, the amount of electricity flowing through a component or a wire. So in this case, the amount of water flowing through the hose is controlled by one of two things. Either you can increase the water pressure by turning up the tap, the potential energy, or you can increase the width or decrease the width of the hose. So if someone comes along and steps on our hose, for example, we're going to reduce the amount of water that the hose is allowing through that hose at any one point, and therefore creating resistance to the current, slowing down the amount of water that will flow through that hose pipe. So for this metaphor, this foot narrowing the hose represents resistance. And it doesn't matter where we stand on the hose, whether it's near the tap or near the open end, the amount of current, the amount of water flowing through it will reduce the same. So current, voltage, and resistance all relate to one another. If one changes, it will have an impact on the other two. So Ohm's law explains this relationship between voltage, current, and resistance. And the formula for Ohm's law is voltage equals current times resistance, with V standing for voltage, I for current, and R for resistance. Ohms is also the unit we use to measure the amount of resistance a material has. So our Ohm's law formula can be rearranged depending on what information we know. So for example, if we know the current and the resistance, we can multiply them together to find out the voltage. Or, for example, if we know the voltage of a battery is 9 volts and a particular LED has a maximum current of 20 milliamps or 0.02 amps, then we can work out the resistance needed to achieve that current. So to use Ohm's law, first we need to clarify what we already know. Now in this situation we know the voltage and we know the current. So what we're going to look at is R equals V over I. Now if we put in the 9 volts and the 0.02 amps, we must use amps, not milliamps. We can very quickly and easily calculate that we need a 450 ohm resistance. So if we're going to power our LED with a 9 volt battery, we don't want it to blow, so we need to use a 450 ohm resistor to keep that current at 20 milliamps. So resistors are components that we use to reduce the current in a circuit. Now the stripes you see on this resistor show us the value of that resistor, so how much resistance that component has. So each color represents a number or a value, as shown in this table. So to read the value of a resistor, we need to hold it so that the single band is on the right hand side, and the 3 or 4 bands that are grouped together are on the left. So if we start with the band that is on the far left, this represents the first number of our value. In this case it's yellow, so if we look at our table, that indicates a 4. The second band represents the second number, and then the final band represents the number of zeros that we add on to the end. So in this case, brown represents 1 0, so we have our number is 4, 5, and then add 1 0 to make 450 ohms. The final band is a tolerance, so how accurate our resistor is. So in the case of this resistor, it has a silver band, which means it has an accuracy or a tolerance of plus or minus 10% of the value. So although this resistor has a value of 450 ohms, it could be 10% higher or 10% lower than 450. So it could actually range from 405 to 495 ohms. We need to consider that when choosing our resistor. Thank you for watching our video. If you have any requests for future videos or any feedback, please do leave comments in the comment section.